All righty. Can you hear me okay? Yeah. Awesome. All righty. I've been informed there's a clicker, so let's click. My name is Andreas. I'm going to talk a little bit about this demo that you saw and how we made it, but really it's not about making demos, it's about how to take something away from this, right? How do we take constraints like this and make our day-to-day better? So like I said, my name's Andreas. I work in Insomniac Games. I hadn't spoiled that. I'm a member of this demo group, the Black Lotus. It's been around for a long time. It's an Amiga demo group. And I was thinking about that. We were listening to the fireside chat here, right? How do we get people to be curious, right? I grew up with a computer that didn't really do anything. When you turn it on, all you could do was program it. And I think that's part of it, like part of what we've lost. So what are we going to talk about today? We're going to talk about what you just saw ran on a machine from the 80s, right? A tiny ass slow machine. So we did this as professionals, right, in the games industry recently. So what is it that we can bring back and what is it that we can bring forward? So really, day to day, right, what's the connection? And, you know, to have a bit of fun. So let's talk about this machine, right? We did a show of hands. There's some people who know an Amiga. That's good. The first thing to know about this is that it says 87 on the can, but really it was designed in 1985. It's virtually identical to the Amiga 1000, which was the Commodore Amiga. It's kind of old. So we're rocking a 7.16 megahertz Motorola 68K CPU. The thing about the Amiga and why people love it, and I still do, is because it was a really, really cool machine. It was way ahead of its time when it came to hardware design. It's a DMA-based machine, and you have DMA channels that you program. And compared to most 80s computers, it was completely revolutionary. So the stock config here, like that you got when you bought this thing, this wedge-shaped beauty, it's half a meg RAM, 512K, of what's called chip RAM on the Amiga, which is RAM where you can put graphics and music and have the custom chips do something with them. And almost everyone would add like another half meg to it, so they would have some space for their code and stuff. So I'm not going to bore you with a super long introduction here, but like, what is this demo thing that we're talking about? Well, you know, believe it or not, but people copy software, and it's like a bad thing. In the 80s, this was rampant, right? And in order to copy a game, you need to crack it and remove the copy protection, so people did. And they would put their little tag on it, say like, I cracked this, I'm cool. And that was called an intro, right? And this became like an art form in itself, where people did more and more of this. And like, it wasn't really about cracking games anymore, but showing how cool you were. So you basically have all these groups of people who know the hardware really well, and they're trying to basically one-up each other. Like, well, you know, we're going to do that effect you did, but we're just going to do it twice as big or twice as fast, right? Style and flair. So over the years, right, you can see how this is, you know, a big bragging match. So it has evolved to become like an art form and digital heritage, I think now. So if you make a demo, what do? Well, you go to a demo party to show it off. And so this is where the remaining people who seem to get fewer and fewer every year because we're dying of age, but this is where we go to show off and have competitions and stuff. And if you ever want to go to a demo party, it's a lot of fun. It's super welcoming, just like this event. The biggest one is in Germany every Easter. It's called Revision. And if you go, you'll find that it's a multi-day event. There are multiple tracks, competitions, right? So if you make a music track, you can go participate in that, or there are, you know, 4 kilobyte intro competitions and all kinds of stuff. And also old school demo competitions, which is some of the stuff we're looking at here today. So if you want to make an Amiga OCS demo, OCS is old chipset, you're going to have a demo like this one that runs on an Amiga 500. We're in Europe, so it's going to be PAL, 50 hertz. You're going to have half a meg of chip mem and half a meg of fast mem. That's it. And you're going to have to deliver it on 2 floppy disks, which are 880K. That's it. Like, this is what people had in their bedroom in the 80s. So, I mean, I certainly did. Like, it's worth pointing out here, these are hard constraints, right? You can't show up with your demo running like ass and saying, I need a faster CPU. Like, that's not going to happen. Like, this is the thing you're going to run on. So this demo, in 2015, we were sitting around bitching about how terrible demos were because they had turned into sort of like a joke entry for the Amiga OCS competition. And so my dear friend Daniel had a plan. He said, here's what we should do. We should just make so much 3D that it's ridiculous and everyone else can just go home. Right? There should not be a way to compete. And we're going to just use everything we know and have learned from 20 years as professional game developers to make this happen. And, you know, that doesn't seem too bad. All right, so now you know a little bit about this. Let's start talking about that CPU. So a lot of people here probably haven't programmed a 7 megahertz CPU. So in a word, I mean, I know how slow the CPU is, but just for everyone here's benefit, I took the reference MD5 code, like you'd probably see it, it's some RSA code. And I MD5'd 800 kilobytes of data, right? So I have a slow-ass Surface laptop from like a few years ago, and I have my Amiga 500. So it's 2 milliseconds on the laptop, which is slow by today's standard, and it's half a minute on the Amiga, right? So we're talking 4 orders of magnitude, like at least 10,000 times slower than what you're using for your data driving. This is 1 core, right? So if you were to use like SIMD instructions or actually think about the cache or use more than 1 core, Like, it's ridiculous. That's how slow it is. So how are we going to realize this dream? Well, we've seen that this is ridiculously slow. Clearly, we're not going to do this with the CPU, right? The cool thing about the Amiga is that most of the power is in the custom chips. But I say power, right? But here's some numbers for you. There's a blitter, and it can clear and fill and do stuff like that. So we figured out that it can do 3-bit planes at the target resolution in about 1.5 of these 50 hertz frames. The CPU, we can write some really optimized code to draw most of the lines we're going to need for these contours. And we have no CPU budget left. So we can't transform, we can't do math. Like a multiply on this machine is between 18 and 36 cycles, and those cycles are slow. So we have to really tighten this up. So one asset that we have is, you can do 3D sort of on the Amiga, right? It doesn't have 3D hardware, it's not a GPU, but the blitter can assist you. So what you do is you draw special lines in a buffer, and they have 1 dot per scan line. So it looks something like this. You sort of plot one thing per scan line, and then you can run this blitter in a fill mode. And then you repeat that for each bit plane, right? Like most machines from the 80s, this is a bit plane based kind of thing. So you add 1 more bit plane, you double the number of colors you can have. So the machine can address up to 6 of those, but 3 is like the sweet spot if you want to run anything in real time. So here we get to the first kind of point that we can think about. We're going to have our blitter fill and clear at maximum speed, like we know what the hardware can do. We're going to have our CPU draw lines at maximum speed, right? And the blitter is going to help out here. And we can sort of figure out the budget for how much we can do in a frame, right? And then we're going to pack streams of outlines for these 3D scenes onto disk. We didn't know how to do that yet. But we know what we needed. We needed a demo that was long enough to win a demo competition. It had to be impressive so everyone else could go home, right? So, and we know that we didn't have any CPU time left. So that gives you kind of a budget, right? We have to fit on 2 disks. We have to do this, like it has to be this, right? And this is our first takeaway here. Always work backwards from the desired outcome to inform and discover the constraints that you have, right? And in general, to maximize the benefit of anything that you're doing, assume for a moment that it's working at peak efficiency, right? You have a thing that is doing exactly the best that it can do. What has to be there for it to be able to do so? Like, what data do you have to have already? How do you need to update it, etc. This one may be obvious if you have a CPU that's 10,000 times slower than the one that you have offline, is don't do at runtime what you can do at compile time or build time, right? And I want to, this is obvious maybe, right? But it really paints a picture when you have a machine that's this slow. So to the runtime, it doesn't really matter how you came up with that data, if you think about it. If you have an algorithm, you have something that you want to test, you can prove it out using fake data, right? Put some shit in a buffer, right? Assume you're going to be able to make data later. So case in point here, like the scene drawing and actually working backwards from the constraints here took us, a couple of weeks to figure out, and the tooling to actually make this data took 4 years. Because it turns out it's a hard problem. Anyway, if you decide to make a demo for the Amiga, you have a couple of ways to do it. You could write a program, right? And you could let the operating system load that. And here's the problem. You have 1 meg of RAM, and the OS is going to use a bunch of that. And all your stuff has to fit into that one program, which is not awesome. So what you saw here is like you plop in a floppy drive, and the machine just goes, right? So the best Amiga 500 demos are tracked loading, as it's called. So they're pulling in code and data as they're running. Which, to teenage me, seeing this from my heroes was pretty awesome. Like, it seemed like magic. So let's look at this for a minute. Basically, the first 1K of a drive, like the 2 first sectors of 512 bytes, that's your boot sector. So they get loaded into RAM, and then the CPU is just dropped in there. And you have some OS stuff you could do to bootstrap, but you're basically on your own. So what we do is we load this control software here that multiplexes everything that you see, right? There's an effect that you're seeing, but there's a lot of stuff going on in the background to prepare for the next thing you're going to see. So loading, decompression, stuff. We're going to look at some of that later. Sound mixing, because the song that you're hearing is bigger than what would fit in RAM. So we're mixing drum samples, like as we're going. So we're basically building an OS specifically dedicated to showing you this demo, right? What could possibly go wrong? Okay, so let's talk about some more nitty-gritty stuff. Memory management. I said we have 1 meg of RAM. We have two 512K blocks, right, that we need to manage separately because one is for code and one is for sort of data that the graphics chips can get at. All right, another constraint, we have one thing you're looking at and one thing that's coming up, always, okay? Here's the thing that may not be obvious. You can then use a ping pong allocator, right, between the low and high parts of each of those buffers. And we basically made it so that nothing can allocate dynamic memory. It's all static buffers. Why would we do such a thing? Well, because we know that it's a constraint that these things have to fit in memory at the same time. Why would we make them allocate memory and find out at runtime that it didn't work if they were too big, which they were during development, right? So if we statically allocate everything, we can check at build time if two things are going to fit in memory at the same time. That's cool. That means that you don't have to wait for a minute to see if it worked. In fact, the entire memory allocator is so simple, it uses advanced addition and subtraction technology. I can show it right here on the screen. So in one case, you have an active part, right, that's running, and you're preparing the top of the memory half for the next part, so you're allocating from the top down. And in the other case, believe it or not, we're allocating from the bottom up, right? It's so simple that a child could write it. Which is my next takeaway. You don't want to solve for problems you don't have, right? We could have used a memory heap to manage the memory for this. I mean, it'd be dumb, but we could have, but it would just buy us more problems and it would be slower. Why could we get away with this? Because it's not interactive and it does the same thing every time it runs. So there are no what-if questions that anyone could have asked, like what if this or what if that? Doesn't matter. You know, what if the CPU were faster? That's great. We're just going to busy wait and slow it down. My point in bringing this up, even though it's a silly distraction, is if you look at a lot of the stuff that you're making day to day, you'll find the same thing. It always does the same thing in practice, right? And there's a bunch of generality built in that doesn't actually need to be there. And I think this is a trap we fall into. We heard some of it here in the chat earlier. We overgeneralize because we're taught to do so, right? And so my message here is trust instead that if it is not what you want, you can delete it and do something else, right? Rather than trying to come up with a solution that could cope with anything, just make it cope with the thing you actually have right in front of you and then delete it and do something else. I'm arguing that that's cheaper than trying to come up with an anticipatory solution. So I know this probably makes some people uncomfortable, maybe not in this audience, but in other audiences. But here's, like, if you're unsure, and I did this for a while just to cleanse my own palate, put a comment at the top of the file that says, do the simplest thing that can possibly work, right? Do that thing, and then when it sucks, come back and delete it. And if you're extra unsure, you have my permission. It's okay. All right, let's talk about compression. So the 3D scenes, like the sort of pièce de résistance of the demo, they use custom compression stuff. So I'm not going to go into those, but everything else uses LC4. But with one caveat. Remember, we don't have a lot of RAM. So we can't afford to keep both the compressed and the decompressed data in memory at the same time. It's just too big. So we need in-place decompression. This means that decompression is going to chase kind of the tail of where the compressed data lives. And that's not always safe to do with like an LC-based compressor, which is like a match and copy type thing. So again, you'll start to see a theme here. Work out of build time, what margin must be applied to make this safe, right? Which means we're basically looking at the compressed data and then we're stepping the LC4 decompressor virtually, right? To figure out what it's going to do eventually when it runs on the machine, so we can find safe points to interrupt it, and therefore like we can juggle these blocks. So let me show you a visual here of what I mean. Let's say that this is the target buffer. We're going to put some stuff in here. So we're going to stream compressed data to the top of that buffer, right? Here's a couple of blocks. And while that's going, we're going to start decompressing to the bottom of the buffer, right? So you see here what I mean by the head chasing the tail, as it were. And by the end of it, you've sort of done this, right? And you need to figure out how it's safe to do so and where it's safe to interrupt so you can have it in the same buffer. If you know anything about LC4, like it's like an LC type algorithm, so you're either copying a literal or you're copying a match. So what you have to avoid is breaking out at the wrong place, basically, and then trashing some data and then copying in the wrong thing. So what we do is we burn through it. I'll show you the code here in a minute. And then figure out a few places where we'd like to be able to interrupt it as we're streaming, and then we put that in a table. So here you go. You don't have to take notes, but if you want this, you can find it later. But LC4 is such a simple format that you can basically simulate unpacking the whole thing and figuring out that these byte offsets is like where we would want to break the compression. My point being that you end up with a loop that looks like this, right? Load some data, like take blind directions from a table with no error checking, load some data and decompress it. Just blindly trust what's in the table. And it's trivial, and it's fast, and it runs on an Amiga 500. So here's my fourth point that I want to drill home. Just because it's LC4 doesn't mean you can't change it or do something slightly different with it, right? We're still using the LC4 like high quality compressor, but we wrote our own decompressor and we split it and tiled it and did all kinds of stuff. Software is not set in stone, right? It's a thing. It's the idea that's valuable, not the reference code. If you end up like with a small table and you don't even bother with error checking because you've proven that it's right, you're doing something right. Like, this is good. So I don't know if you've noticed a theme here, but we're doing the slow analysis offline where we can afford to do it. And at runtime, we're just blindly trusting a table. So here's another fun detour. So by now you have to realize that there's a lot of stuff going on more than just the thing you're looking at, right? And so I alluded to this before, but there's floppy DMA going at all times. And floppy DMA, like it moves stuff from the floppy drive for you, but you get frequency modulated data that you need to decode yourself. There's also the state machine of what's going on. There's drum loop sample mixing, like I mentioned, it doesn't fit in RAM without this. We're doing decompression, and we're initializing what's about to come next. How do you do this with one CPU, no operating system? So, I'm sorry, there's no magic. Like we've not involved anything new here, but it's interrupt-based programming. So if you're not a kernel developer or like an old-timey person like me, you may have not used this. You can think of it as a function call, but it also saves the flags, right? If you were to insert a function call at random somewhere in between two instructions, it would kind of be an interrupt. Like that's kind of how it works. So on the Amiga, I use these for a lot of things, right? If you want to do something in sync with the screen update, you can have a coprocessor, a raster interrupt. You can do interrupts when the blitter is finished doing something or when the floppy DMA is done, stuff like that. All right, so that's great. I guess we can interleave some stuff and do frame-based updates, but we need way more, like we looked at, like we have all this other junk going on. And what we didn't want to do was write a bunch of cooperative kind of multitasking code. Like maybe you've done this, or like maybe you've had the misfortune of having to write something like this, Or like, I'm doing this really slow thing, but I also need to go check if something else wants attention, right? And all of a sudden you have this kind of economy where you're trying to figure out how cheap is the smallest thing that I can do without being bothered checking if someone else wants in. It's awful and slow and complicated. So, you know, what operating systems know, and you know what we know as Amiga programmers is, you can task switch between stuff with an interrupt. All you do is you return to somewhere else, right? So I'll show you in a moment, but it looks like this. So top here is the top of the frame. We get a vertical blank interrupt, and we do some housekeeping, and we switch to the main part update. Like whatever you're looking at has to render, right? And it voluntarily yields sort of like a fiber or thread in a modern operating system context, right? And whatever the loading framework is doing, like whether it be decompression or MFM decoding or drum sample mixing, like that happens. And then at the top of the frame, you reset and switch back. So in some glorious 68K assembly, that's this right here, right? Stash the registers on this one stack and then swap the stack. I'm bringing this up as a novelty, like at 68K assembly, but it's exactly the same thing as your operating system is doing every day. So the idea is solid, like it's not new. The only real difference between an interrupt and a function call is that you have to pull the flags. So that's why it's a RTE instead of RTS. Another topic is, we've seen how this thing is slow, right? Back in the day, if you were to sit down and write a track loading demo like this on the hardware, like power to you, but it would not be an amazing experience. I guess we didn't know better back then, but we do now. Like, there's no profiler, there's no debugger, shit is slow, and to test things, like you give up your IDE because you're typing on the machine, but remember, we're throwing away the operating system and booting from scratch, right? So you have to wait for a minute to see if it worked. It's not amazing. So what we did was we took an emulator and we hacked it up to bits. And we made kind of our own emulated machine that we ran. So here's what we added to the emulator. High resolution timers, which you can't really do on the hardware. It has low resolution timers, but nothing like cycle accurate timers. This means we can do cycle accurate profiling. We added printf logging. So the emulated target can printf to the emulator console, and the emulator is doing all the formatting of arguments and stuff like that. We added memory protection. That was nice. You know, imagine being able to crash when a stray DMA writes to the wrong buffer. Like, that would be nice in the 80s, and it was a reality when we did this demo. Like I said, the machine is super slow, so if you just want to fast forward and skip something, there's something called warp mode, and we can control that from the target, so we skip over like long, boring boots and stuff like that. And we taught the debugger to load symbols for the parts, so we can actually use the like whole machine debugger in the emulator as if it were like a target debugger. So call traps are what we used for some of this, which is, it looks weird, like it's basically the 68K side is just taking a jump to some fixed address, like do this. And the emulator traps this and does whatever it wants to do. So it's a very small impact on the emulated target, but it's really powerful because you can do a bunch of stuff. And then, why I wanted to bring this up, and we'll get to a bigger point later, but it's unconventional to do it this way because your emulator and your target are cooperating, right? That's the point that I wanted to bring up here, which is okay. Like, we control both sides, right? And we didn't do it because we were doing an emulation. We were doing it because we were making a demo. And that's my point here, like takeaway number 5 is, if you emulate a problem, right, by ripping it away from where it should be and putting it somewhere else where you can study it under a microscope, you can actually do things that you couldn't before. This goes way beyond retro hardware, right? If you use Valgrind, for example, like to track memory accesses under Linux, it sets up a virtual CPU, which is part of why it's slow. I did a cache simulator a few years ago that does the same thing. Like it's single steps x86 code so that we can simulate whatever memory accesses it would make. In both of those cases, and indeed in our demo case, it allows you to reformulate the problem, right? All of a sudden we can do cycle accurate profiling. Great, like you can't really do that otherwise. So here's some odds and ends I want to bring up. We needed something like BSS, like zero-filled sections and executables, but we didn't want to pay for the zero filling because, again, slow CPU. We were actually wasting time zero-filling buffers that we were going to render into. Like, kind of dumb, right? What's the fix for this? Write a linker. No big deal. We were trashing registers because, I mean, most of this demo is assembly code. Like, there's some very high-level glue in C, but the rest is just assembly code. And so you have a bunch of people writing assembly together for years. You're going to trash registers, and it's not going to be a good time. So we wrote a front end to the assembler that allocates registers, right? And it just filters out the assembly code the other end. Here's another takeaway. When something isn't changing, right, we're targeting this CPU. Like, no time fairy is going to come change any of that. In fact, then, anything that you invest in that tooling is by definition not throwaway. Right? It's a fact. It's not changing. And the other thing is solving for just the problem that you have, right? We're not writing a whole program optimizing linker here. I'm writing some shit to slap some sections together and call it a day. Like, it took me a couple of days, right? Same thing with this register allocating assembler. It's also a couple of days. Like, because it doesn't solve everyone's problem. It solves my problem. Okay, so we've done a kind of tour of some of the issues that we had doing this demo, right? But we're all here not because we're demo programmers, I guess. Well, most of us aren't. But we don't work on 7 megahertz machines. We have more than 1 meg of RAM. What are the lessons and how do we take it to our day-to-day? So one thing I want to talk about is this idea of back pressure, which is a fancy way of saying that resources are finite and you don't have infinite memory. Think about it this way. A system is always bound by the slowest component, right? That's going to hold up your throughput, whatever it is. If it can't keep up, you have to stall or fail people who are trying to put more work on it. So consider this like consumer producer type problem, like with thread pooling or work queues or whatever. If you're producing more stuff than your consumer can eat, what are you going to do with it? And here's, speaking of why we need this conference, if you look at a lot of libraries that try to do this, they just buffer shit on the heap and return. Great. Like, what? So there's no back pressure, and after a while you run out of memory. Won't work. And if you look and squint, you see this problem everywhere, whether it's work items in a queue, or buffers, or ring buffers, or temp file space, for that matter, or logging, right? It's important to find a way to solve this problem in system design, right? What happens when I can't keep up? And a lot of times people just YOLO this. So, and let me tell you, having something very, very slow makes this really evident when you've screwed it up. So, maybe consider using an Amiga. Finding or inventing constraints is another thing I think we should do day to day. A constraint is what allows you to explore a problem end to end. If you can't say what the maximum count is, you have no idea. You don't know what problem you're solving. The good news is you can make a constraint, which is in fact okay, right? And you can make it hard or soft, whatever, as applicable. But it's a fool's errand to say, well, I'm not ready to commit. I'm just going to dynamically grow, right? Then you have, in fact, not solved the problem. So take something like, I'm going to have 1024 dynamic actors, max. Okay, that might seem silly. Like, why would you draw a hard line there? Like, what about 2000? Wouldn't that be cool? Well, it might be, but then you could raise the limit and do the appropriate trade-offs. But if you know what the bounds are, you can now reason about what the worst case is for updating, for sorting, for memory allocation, right? Similarly, let's say you need to run at 120 FPS. Great. Work backwards. Again, you have an 8 millisecond frame. You can start informing other constraints on, here's how much time I can spend on my actor update, or whatever it is. We looked at emulation and playback a little bit, right? By capturing inputs to a system so you can replay them, you can emulate the real world, as it were, right? And put something in a test bench. The thing about this is that it sort of makes you independent from real-time constraints, right? I'm sure a lot of you work with network stuff or with sort of real-time event stuff. Put all that shit in a file and fake it happening. It won't be exactly what's happening in real time, but it'll be good enough and close enough that you can reason about what the bounds are, what the performance numbers are, how you can profile it, what the worst cases are. So it's something I did at work recently, where the group took a build system that took 8 hours to complete something, but 7 hours and 50 minutes of that were something else. So we faked all of that, like just pretend it all just happened, so we could profile what was left, which was the interesting part. Another example is race condition discovery. You see some tools doing this, where you're fuzzing sort of multiple threads by simulating what order you're stepping them in and finding race conditions automatically. This is impossible to do if you're relying on time and luck, right? You need a way to rip it away from that time axis and put it in a test bench. This might be a new point for you. Don't do it on runtime, which you've seen a lot of times in this talk. This goes back to what we were talking about earlier, that it seems like a curse that we're expected to just live with shitty stuff. And when we look at software, and it's like, yeah, it's slow, it takes 10 minutes to run an update on Firefox or whatever. Death by 1,000 cuts is a thing, right? And we sort of, as programmers, find ourselves in a position where we have to be vigilant in code reviews, like there's a better way to do that, right? Or don't waste time, or don't do the thing. And as computers get faster, you can get away with this. 7 megahertz, you can't. So here's some examples that we can take to heart for today, right? Maybe you're comparing strings at runtime. Like maybe just hash those string constants instead of build time and put the hashes in and compare those. Or, you know, stuff like that. Or saying, I can't commit to what's going to be in this thing, so we're going to allocate it out of 1 million small pieces. But we could compute the worst case and allocate that. So some of you will say, like, well, that doesn't apply to me because I have this like dynamic game and I need to tweak everything and like, screw you and your static offline stuff. Right, because then I can't tweak things. To which I say, false. Whatever you use to produce the data that you loaded to do the table-driven small thing, do it again, and then reload the table. Problem solved. And you know what else is cool about this? Like, you don't have to put a bunch of tweak junk in your app or game. Like, that code doesn't need to exist anymore. You don't have to link in shitty IMGUI libraries and like have your designers edit shit inside a game when they'd rather be spending time in Excel or a text editor or whatever. And you don't have to support it. So that seems like a win to me. All right, let's wrap up here. Obviously, there's way, way more to making this demo than what I've covered here. This was kind of a really quick intro for non-demo seekers. It's a lot of fun. If you want to try something like this, go for it. Just be aware that the barrier of entry is crazy high. Some of the more salient points. Remember to work backwards to uncover constraints. Adopt those constraints to make decisions. Don't overgeneralize. Do the slow thing offline and do the fast thing runtime. We did win that demo competition. But it was hard competition. It was a really good field because I guess everyone had thought of the same thing, that wow, this competition seems like a shoe-in. It's like it's really easy to win. So it was a brutal field, but very proud of that achievement. Thank you for having me. Thank you for supporting me, my demo group, and my team at work for enduring me blabbing about all this junk. And let's do some Q&A.
Round of applause.